Circular motion. So I'm going to kind of walk you through how we get to circular motion, and the biggest link comes from projectile motion. So I'm just going to do a few little drawings here. So this is the way that we normally see the world if we were to launch a projectile out. It has this arc to it. All right, so if we fired something out this way and it lands on the ground, X marks the spot, that type of stuff. So we see it has this beautiful arc to it. And if I was to draw a force diagram in a halfway point, we'd say, well, gravity's pulling me down. And if I was to look at my actual velocity, then it's a different color, then my velocity vector is actually tangent to that path. And if I said, well, what's my direction of my acceleration? Well, we'd say, well, acceleration is in this direction because we have unbalanced forces in the y-plane. And that's where we're at. But when you do circular motion, things get a bit different. All right? So we could take the exact same idea, wrong color, we take the exact same idea, and now we're going to kind of launch this object. So I'm going to take the Earth as my example here. So Earth. And I'm going to draw Earth. Oh, look at that picture of the Earth. It's fantastic. It's not even a circle. I don't care. So let's say we were to fire it off here, give the object the same velocity, so maybe it's in our space, and we give it a push. Well, gravity is still going to pull it in, but as it gets pulled in, it still has that tangential velocity, so it still wants to go around. So if we get it just right, if we get this perfect balance, then we're actually going to find that we're not going to hit the Earth at all. So if I was to draw a force diagram here at the bottom of my object, like, I don't know, let's call it the moon, then at all times it's being pulled towards the Earth by gravity, just like our projectile was. So we still have an acceleration that is also heading towards the Earth. So right now everyone's like, oh no, the moon's going to hit the Earth. It's accelerating towards us. Why weren't we told about this? Because no one cares. Because in reality, you have to remember that it also has this tangential velocity. So it's moving out like this. And as long as there is a beautiful balance between how fast it's moving away and how hard it's being pulled in, it's not actually going to come in and smack us. So that's why you haven't seen a death clock or something like that saying, hey, Earth ends in this much time. Because as time passes, let's say the moon, it moves, it rotates, so now it's here. Well, now it's being pulled in like this by the force of gravity. The acceleration is still unbalanced force. We still have an acceleration that's pointing in towards the center of the Earth. And we still have our velocity that is moving tangent to the circle. All right, and it's a nice constant velocity. So as we go around, it's not actually ever going to hit us because of Newton's laws. So Newton's first law of motion says an object in motion wants to stay in motion, where specifically that motion is a straight line path. So every single moment, the moon's like, freedom, and it's running away. But then the Earth says, no, you need to stay with me because it's applying that unbalanced force. So it's being drawn in. All right? So we have a name for this type of force that draws something into a circle instead of a straight line. And we call that a centripetal, centripetal force. Now, this really means the center seeking force. All right? That's what this really means. And so it's the force or forces, because it could be multiple combinations like that make an object travel in a circle instead of a straight line. Because Newton's first law of motion says all objects in motion want to stay in motion. They want to go in a straight line at a constant velocity. unless acted upon by an outside unbalanced force. So here, in this situation, gravity is my outside unbalanced force that is causing, in this case, the moon to go in a circle around the Earth instead of a straight line, because every moment the moon wants to go in a straight line. But this force of gravity is pulling it in towards the center of the Earth. So it ends up going in a circle because of this balance of it wanting to escape, but being pulled in, escape, pulled in. All right. Now, let's say, just for sake of argument, which is also known as reality, if the velocity is too great, then instead of being a perfect circle, you're going to see it starts to spiral out. And this is what's actually happening, is the moon is actually going a little bit too fast for gravity to keep it in perfect circular orbit, so it is slowly, ever so slowly spiraling away from us, which is much better than the alternative. The alternative is if it was not going fast enough, then instead it would be ever so slowly spiraling in towards us, and then we would be sad because it would crush us. All right? So for all the situations we're going to deal with this perfect balance, all right, which we call uniform circular motion, because it has a perfect circle. It's not changing its speed. It's not getting closer or farther away. That's what we're going to deal with. Okay, but in reality, if you don't have that perfection, you're either going to spiral in or you're going to spiral away, depending on what the forces are. All right, so some of the big takeaways that we want to conceptually understand have to do with this drawing over here. So I'm going to do that again. So we've got the center of our circle. We've got a circle close enough for government work. And if you draw an object, at any point, you're going to have a net force that pulls it in towards the center of the circle. All right, so even if I'm down here, I will have some sort of net force that pulls me in towards the center of the circle. All right, and this is what we call our centripetal force. And with that centripetal force, we want to understand that we're going to have acceleration that is parallel to it because it's an unbalanced force. And then we're also going to have a velocity that is tangent. So if I'm going this way, velocity is tangent. So now technically the velocity is changing for us to have acceleration because the direction is changing. So what we're really going to treat in our equations as you see them come up, we're going to use the word speed, but we're still going to use the symbol v for velocity. And that's the way we kind of decide it in the world of physics, I guess. But it is still accelerating because your velocity is changing because your direction is changing. So that's something you want to definitely make sure you keep in mind as you go about solving these types of problems. So again, the key idea is centripetal means center seeking. So if we talk about centripetal acceleration, it is the acceleration that points to the center of the circle. If we talk about centripetal force, then we are talking about the force that's pointing in towards the center of the circle. And velocity is always tangent to the circle. So velocity or speed is tangent. And then if you look at the orientation, the acceleration is perpendicular to the velocity. So these are some of the fundamental things that we need to keep in mind. Now, one last thing, since we're here just talking about general overview, we haven't got any equations. If you ever see this, run screaming. All right, centrifugal or centrifugal is referring to an outwards pointing force. And fundamentally, if you draw a force diagram, which we've done a bunch of times here, this is not true. Now, you can redo your frame of reference and kind of get an implied thing, but the reason why this is a thing is because people will say, oh man, I was spinning in a circle and then I was flung outside the merry-go-round. And then I go, no. At every moment, your body wanted to go in a straight line, and you were holding on to that merry-go-round, so you were forcing it to go in a circle. And when you couldn't hold on anymore, you let go, so you did what you were always supposed to do, which was go in a straight line. So this here is fundamentally a lie. L-I-E spells lie. Giant lie. All right, so the way I remember this is if you have an F, that means you failed physics. And if you have a P, that means that you passed physics. So again, this is a giant no-no that we're not going to deal with. So, whoop, no. All right, no centrifugal forces in my class. All right, so these are the fundamental concepts that we're going to build upon throughout the unit. Have fun!